We're in the last chapter. We talked briefly about dark matter last time. I think that we're probably pretty good with that for the time being. Maybe I'll go into a little bit of dark matter, maybe 20 minutes on it. Complexity and chaos, that should be interesting. High temperature superconductors, and some questions we know to ask. So with that in mind, since there are quite a few topics that we want to address, we will go ahead and get started. Let's see, Kirk has gone up. When is my turn to go up on the, whatever it's called, the something or other thing? It's probably never. Let's go through the text, just so that I know some of the things that are talking about. We'll touch lightly on a few things, and we'll go into depth on a few things, and that will be it. So superstrings, oh, that's all I got for superstrings? Okay, well, that's not very interesting. There are a variety of different things that can produce superstrings. One of them is topological defects, where you have boundaries of, like, the universe spawns and certain constants exist in certain places. They might not agree with each other, or there might be slightly different properties from one place to another, and there will be domain walls between these different regions. For example, depending on what the dark matter is, if you have the misalignment angle for the axion field is different in different regions, then you can get a boundary between a place where the axion field has one misalignment angle here and a different misalignment angle here, and so that frontier could be like a cosmic stream, like a place where there's energy stored in the fact that there's a transition in the axion field. Anyway, so superstrings, there hasn't been any evidence for them, just that they could exist. Dark matter enclosure. We know about dark matter already, and we've talked about it to some extent. We know the evidence for dark matter comes from the rotation curves of galaxies, although there are other explanations for the rotation curves of galaxies besides dark matter. So it could be, there's one called modified Newtonian gravity that says that maybe the force of gravity, or the acceleration due to gravity, changes as the gravitational field gets weaker. So you cross some threshold where the gravitational field really turns on, and when you get below that threshold, then the gravitational field turns off. It doesn't go to zero, but it slows down. But there are some pieces of evidence that go against MOND, modified Newtonian gravity. One of them is this right here, the bullet cluster. Now, there is a video from Sabine Hassenfelder, I think is her last name. Sabine is her first name. That's what it's easier to pronounce, so that's what I'll go by. Where she says that this is actually evidence against dark matter. I'd have to sit down and talk with her and see if there's where the points of disagreement are, because I think that this is actually in support of dark matter, because what's shown here is the fact that the gravitational lensing, the mass for the gravitational lensing that you get from this cluster. So it's a cluster of galaxies, and in that cluster of galaxies you have, let me zoom in a bit so that we can see it up close and personal. You have a weak lensing signal that indicates where the mass is located, and then you have this X-ray signal that tells you where the gas is located. So the idea here is that you have these two clusters of galaxies that have passed through each other. The dark matter with a very small interaction cross-section is able to pass through without building up any pressure. It's not pressure supported, it's collisionless. And so as these two galaxies pass through each other, most of the mass stays with the dark matter. And so the gravitational lensing signal will follow the dark matter, where the gas that surrounds it, so each of these galaxies has a halo of hot gas. As they pass each other, the gas does have a high interaction cross-section, and so smashes into itself and basically gets stuck. So you have these two clouds of gas that come together, and then they bump into each other and they stay there. And so that's this hot gas that we see here. Hold on, let me switch the size of my pointer. I need to pull up the settings. Anyway, so this is the bullet cluster, and it is used as strong evidence for the existence of dark matter. All right, get ready for this pointer. Here it comes. Here it comes. There, check that out. Okay, so that is the bullet cluster. There's another cluster that is similar to this, where we're looking more down the line of the collision. But anyway, so there's that. All right, what else? So that's dark matter. There are different possibilities for what dark matter is in terms of whether it's, we've already talked about MOND. It could be axions, which is, of course, everyone's favorite dark matter. I have several videos where we discuss that. It could be WIMPs, which is weakly interacting massive particles. I mentioned before that it could be machos, massive compact halo objects, as long as the machos are the right size. Even though now I don't think that machos can be all of the dark matter. I think that it can only comprise a portion of the dark matter. But anyways, there's that. Machos right here, see, massive compact halo objects. To date, few machos have been observed, but not predominantly in galactic halos, nor in the numbers needed to explain dark matter, which is essentially the rotation curves of galaxies. Neutrino oscillations. We've talked about neutrino oscillations because neutrinos are amazing like that. There are another type of dark matter, weakly. Oh, so this is basically saying that neutrinos are not the dark matter. Neutrinos would be considered hot dark matter. So there's hot dark matter and cold dark matter. The prevailing model for the universe is the lambda CDM, lambda, which is the cosmological constant. So cosmological constant, cold dark matter, lambda CDM. The cosmological constant could have, which is like dark energy, could have some physical origin. It could have some geometric origin, like meaning that it could come from the geometries, like general relativity and the metric. It could come from some fundamental particle interaction for a particle that's yet undiscovered, or maybe that has been discovered, but it's some property of those particles that's yet undiscovered. But anyways, the point being that neutrinos cannot be the dark matter. They can contribute a portion to the dark matter, at least the neutrinos that we know and love, the three main types of neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino, they do contribute some to the total energy budget of the universe, but not very much. And they move too fast. So cold dark matter means that the dark matter particles are moving very slowly, which is like tens to hundreds of kilometers per second, which might not seem very slow, but it is slow compared to the speed of light, which is hundreds of thousands of kilometers per second. And so neutrinos move close to the speed of light, and so they would be considered hot dark matter. So the prevailing model is cold dark matter. The reason that we think that cold dark matter is more favorable than hot dark matter is the fact that galaxies, the way that galaxies cluster. If you have hot dark matter, then the matter is moving too fast to form really compact objects, like compact in the size of galaxies. You have to have cold dark matter that's able to settle down to something the size of galaxies. If the things are moving too fast, if the dark matter is moving too fast, then the halos get too big and fluffy. Okay. There are things, here's Axions. Look, this is definitely a good textbook. If they mention Axions, then that's good in my book. If they mention, especially if they do it in positive light. Neutralinos, this is an extension to the standard model where not only do you have these quarks and stuff like that, but each of those quarks has some superpartner and the quarks are fermions and the superpartners are bosons and they're more massive, and the lightest supersymmetric partner is one of them is called the neutralino, but you could have other ones like the gravitino, something like that. If supersymmetry is real, then there's a whole new host of fundamental particles that could be the dark matter. That just none of them have been detected yet, despite our efforts over the last 20. Well, when was the real dark matter detection? Probably was the late 90s when things really started coming out and ramping up to what we have today. All right, so that is dark matter. Complexity and chaos. Let's see what this... So there are physical systems that exhibit chaos, meaning that small changes to the initial conditions can produce large changes in the outcomes. So let me give you a prime example of a system where small changes in the initial condition can cause large changes in those outcomes. All right, is everybody ready for this? Be prepared to be amazed. It is called the pendulum, the solid pendulum or the rigid pendulum. Okay, if you have a pendulum and that pendulum is suspended by a string or a stick like this. So here's the pendulum and you swing side to side. Wow, what an ugly graph, ugly drawing, but it's okay, that's the one we've got. So here's this pendulum and it swings side to side. If you take this pendulum and you displace it slightly to the side, so you have the same pendulum but you start it a little bit farther away, what you'll find is that especially at small angles, when the oscillation angle is really small, you'll find that it basically behaves the same. It's the same oscillation period, it just has a slightly larger amplitude. So small changes in the initial condition to the pendulum correspond to small changes in the behavior of the pendulum over time. That's true in this situation. However, if you increase the amplitude that you started, then things start to change. Okay, so if we increase, wow, that's so ugly. All right, let me draw this again. If we increase the amplitude a lot, then, so now it's oscillating like this back and forth. The oscillation period is larger, much larger than if it's down here. Okay, so this is the minimum oscillation period, and for most small angles, the oscillation period is going to be the same from side to side as for small displacements. But as you increase the amplitude, then the period slowly starts to evolve and then rapidly starts to evolve, such that here, by the time you get to a pendulum where you start it up like this, so it has to be a rigid pendulum so that it actually works. If you start the pendulum swinging from way up at this amplitude, back and forth like this, it can get you can have a really long oscillation period. And if you displace it even further, so now you're displacing it and starting it from up here, then the difference gets even bigger, such that it will sit there and swing back and forth like this, and this one, after a few minutes, could be on the opposite side of the starting point, because this oscillation period near the top is much longer than the one as you get farther away from the top. And the extreme example of this is if you start this pendulum, not like that, if you start this pendulum completely vertically. So if the pendulum starts vertically, it will stay in the vertical position forever, unless it yields to the enticing of some kind of ambient, like quantum fluctuation or disturbance or something like that. So it's an unstable equilibrium, but it is still an equilibrium point. And so if you have this pendulum upside down like this, and it's perfectly vertical, it will stay perfectly vertical forever. So it has an infinite oscillation period. And if you displace it even a little bit to the side, you go from an infinite oscillation period to just a long oscillation period, as it would swing back and forth like this. And so this is an example of how small changes in the initial condition can produce very large differences in the long run, in the overall evolution of the system. That is chaos. Okay, so most times when people talk about chaos, they don't talk about the chaos from a single pendulum, but instead they talk about chaos from a coupled pendulum, typically one where you have a pendulum like this, and then you have a second one like this, and then you get them oscillating with respect to each other. So that is at least the beginnings of chaos. Other places where chaos shows up is when you have a system that wants to be in two different places at the same time. So I'll give you an example of that. In the solar system, here is the sun. Here's the sun. Mercury has an orbit. Here's Mercury's orbit. Mercury's orbit precesses, meaning that over time, Mercury's orbit kind of traces out a figure that looks something like this. This is highly exaggerated. Okay, so Mercury, it's got an eccentric orbit, and it traces out some kind of shape like that. Jupiter also is on this big orbit. So here's Jupiter's orbit. It also has some small eccentricity, and it also traces out a path that looks something like that. Okay, so Jupiter, its orbit also precesses like this. The thing is that the rate that Jupiter's orbit precesses around the sun and the rate that Mercury's orbit precesses around the sun are almost identical. So one of them is called, I think Jupiter's like the new 6 or something like that. Wait, no, that's not the, I'm not going to give it the name because I don't really know the nomenclature of all the secular resonances in the solar system. But it has some precession rate. I believe it's called the new 5. Jupiter's the 5th planet, and that is the rate of precession of its orbit. But don't quote me on that. I believe it is called the new 5. So the rate that Jupiter precesses around and the rate that Mercury precesses around are almost the same, but not quite the same. And as a consequence, what you have is the solar system that wants to resonate, or it has a natural frequency at two very nearby places. Okay? And so the solar system, if you look at the frequencies that are naturally occurring within the solar system, you have two that are right next to each other. So this is like the response of the solar system. And you can see that these things overlap with each other. what happens is, because Mercury is such a wimp as far as planets are concerned, it would like to sit here and precess at this rate, but it's being driven by Jupiter forcing it. So Jupiter exerts a force through gravity. It's being driven at this rate that's nearby. And so Mercury will actually sit and bounce back and forth between these precession frequencies. Actually, what happens is the eccentricity gets excited. I wonder if that's actually the cause of the eccentricity that Mercury has. I think it's plausible, if not realistically. So the shape of these resonances, I actually drew them kind of upside down. The shape of these resonances actually looks like this. So this is for mean motion resonances, but other resonances can have similar shapes, where at the eccentricity, as the eccentricity gets larger, and this is the frequencies, then the frequency where the resonance happens the frequency range over which the resonance happens can widen. So what's going on with Mercury is that it wants to precess at this frequency right here. It wants to have its own way of going around the sun, and that's driven mostly by the sun's the fact that the sun is an M&M shaped thing. It's an oblate spheroid. Jupiter drives it at this frequency, which is nearby but not identical to it. Jupiter isn't really affected by Mercury, but Mercury is affected by Jupiter because Mercury is 1,000 times less massive than Jupiter. So Mercury will sit here precessing at this rate, but it's got a kind of a high eccentricity, and it will actually kind of slosh back and forth between the behavior of it being in this position and in that position. One of the things that this does is it moving back and forth. It's easier for it to move back and forth if it is up here at higher eccentricity. At low eccentricity, it has to overcome, if it's driven or circulating at this rate, and Jupiter's driving at this other rate, if it wants to jump into this kind of behavior, it has to cross this middle ground where it kind of decouples from the system. And so it's harder for it to transition back and forth at low eccentricity. But at high eccentricity, these resonances can overlap, and so it's easier for it to bounce back and forth between them. That drives the eccentricity of Mercury up. Well, eventually, the eccentricity of Mercury can get so large that it could cross the orbit of Venus. And this was studied by Jacques Lascar from the observatory in Paris, Lascar, Mercury solar system. Oh, I spelled it wrong. I apologize. All right, we're going to look at these images and see, where is it? This one right here. This is the one. This is the figure that we want to do. So this is from his Nature paper that he published. This was in the 90s, I think. He's done some follow-up studies, but this is still kind of the image to look at. This shows the eccentricity of Mercury as a function of time. So time is on the horizontal axis, beginning today and evolving into the future. So this is beginning today, and this is the future. 5,000 mega years from now. That's 5 billion years from now. That's when the sun dies. So the sun is dead at the end. So the question is, what is the solar system going to do between now and when the sun goes through its final stages of evolution? So he has these two panels. The top one is without a correction to the gravitational field from Einstein's equations. The bottom one is including general relativity, including Einstein's equations. So this is the one that's more realistic. And what you see is that, what they did is they set up the solar system, and they have Mercury there, and they displace Mercury. They do many, many, many simulations with Mercury displaced slightly from its initial position. And when I say slightly, I mean incredibly slightly, as in like the width of your thumbnail slightly. So they displace Mercury the width of a human thumbnail from one position to another. And then they run the system. These are small changes to the initial conditions. And what happens is that you evolve the system through, like the system evolution diverges, because there are these small changes, and those changes can grow exponentially. Much like with that pendulum that I showed, how small changes to the equilibrium or to the starting position can correspond to very large changes in the oscillation period, and therefore large changes to the oscillation, the differences that you have from adjacent initial conditions or nearby initial conditions. So that's what's going on here. You start with two nearby initial conditions, and then they follow completely different paths as you go into the future. So for the first 100 million years or so, the evolution is very similar. You can see that all these different paths overlap with each other, both with and without general relativity turned on. But then as time evolves, everything spreads apart, and Mercury goes down to small eccentricities, and the eccentricity can grow, and some fraction of the time the eccentricity grows basically without bound. Once you hit up here, then you start smashing into Venus, you start disrupting the orbit of Venus and having it smash into the Earth. It's going to be great. It's going to be fun to watch. There is a very small chance, so this is about 1%. About 1% of their runs go unstable, meaning that Mercury either crashes into the sun, gets ejected out of the solar system, smashes into Venus or Earth. The Earth collisions was a lot more rare, but they still existed. But it's about 1% of the time that the solar system goes unstable. There's a 1% chance that the solar system goes unstable on a time scale of about 1 billion years or so. And so, yes, there's a very, very tiny chance, but not zero, that the solar system will go unstable before the sun goes through the end of its lifetime. And that instability comes from chaos, the fact that small changes in the initial condition causes Mercury to go back and forth between these two resonance frequencies, or to be driven at one resonance frequency that's very near but not exactly equal to the one that it wants to oscillate at or wants to move. And then that causes the eccentricity of the system to grow, or of Mercury to grow, and then you can get kicked out of the system. That's pretty cool. So that's another example of chaos. That's not the only example of chaos. There's all sorts of other examples of chaos, but that's what it is. So that chaotic systems, complex systems cause things like that. Oh, and look, it has the Mandelbrot set. So once you have the Mandelbrot set, then that just means everything is mysterious. All right, superconductors, high temperature superconductors. So superconductivity is the ability to conduct electricity without resistance. Typically, when you have a wire or electrical current, so electrons flowing through some substance. So here's your wire, like this. The wire's made out of stuff. You've got electrons in there. These electrons are going to bump into stuff, right? The electrons in a conductor, say this is copper, the electrons in that conductor act like a gas. For the most, they do have sites that they can bind to, right? There are copper atoms that they're more slightly attracted to, but not strongly attracted to, because the valence electrons are up in the conduction band. I think I've talked about this already, but we'll go over it again. So you have these different elements. They each have their electron orbitals. So here's all the electron orbitals of these, we'll call them copper atoms for the moment. And then you have some electron orbitals that start to overlap with each other. And then you get bands of electron energy levels. These are called conduction bands, and this is a conduction band up here, and then this is an insulating band gap down here. So if your outermost electron is right here next to a band gap, then you're an insulator. You can't conduct electricity very well because you don't have electrons that are up in the conducting band and are essentially free to move anywhere within this structure. So the band gap is the amount of energy that the electron needs to gain in order to be able to move freely within there. If you have a wide band gap insulator, it's a very good insulator. You have to raise it to very high temperatures or excite the electrons to high energies in order to get them to jump over this and into the conduction band where they're free to move. If you have a metal, on the other hand, a metal already has its, well, if you have a conductor, it doesn't necessarily have to be a metal, like some ceramics, or you can have as conductors. But anyways, if you have an electron, a conductor, its outermost electron will already be up in the conduction band, and it's able to move around with very little interaction with the underlying atomic structure of the material. So, whoops, not what I meant to do. All right, so we have a wire. Here is our wire, like this. It's got a bunch of electrons and stuff like that in it. When you impose an electric field on it, these electrons are going to come and they're going to bounce into each other, and they drift, but they drift in kind of a chaotic fashion. They drift at relatively short rates, like centimeters per second kind of thing. But they're going to bump into things, bounce around. That is resistance to the flow of electricity, the fact that they're bumping into stuff. And so if you have any wire, or a naturally occurring wire is going to conduct electricity with some internal resistance just due to the fact that electrons are colliding with things. And the reason that electrons collide with things is because fundamentally electrons are fermions, meaning that they have half-integer spins. And what does that mean? Well, if they have half-integer spins, it means that no two electrons can occupy the same quantum state at the same time. So all the quantum state of this electron must be different than the quantum state of this electron, which means if they come close together, they have to, when they bump into each other, they can't pass through each other, because if they pass through each other, then they would be in the same quantum state at the same time. So they have to make sure that they are on different quantum states, and that resists the freedom of these electrons from moving around. What happens when you cool things down is that the electrons will bind into pairs, spin up and spin down pairs, like this. These are called Cooper pairs. So Cooper pairs are pairs of electrons. Now, if these move as a couple, so they're coupled up, and if they move as a couple, they're no longer spin 1/2 particles, but in fact they are spin 1 particles. If it acts like a single particle, it now is a particle with integer spin, either spin 1 or spin 0, depending on how the spins are oriented. Like you could have them spinning the same way, but that's a slightly excited state compared to when they're flipped over. And since this typically happens at low temperatures, so you cool them down so that the random motions are very small, and then you can get this weak but non-zero coupling between the electrons. So you basically converted individual electrons that are fermions and therefore obey the Pauli exclusion principle that they can only occupy a single quantum state, or that only one particle can occupy any given quantum state. Now you've paired them up so that they act like photons. You can have all the photons in a single quantum state. So now these pairs can actually pass through each other as long as they maintain their integrity, because now they are integer spin and are bosons and can have the same quantum state as their neighbors. So then when you apply this electric field, these things can move through each other, past each other, without bumping into each other. And so the electrical resistance goes to 0. So the internal resistance of the wire goes to 0. And so they become superconductors, not regular conductors where the electrons are just up in the band and they can move around relatively freely, but super duper conductors, meaning that there's no resistance at all. When you have no resistance, you can really crank up the electric currents in there because there's nothing slowing it down. The resistance itself, when these electrons, under normal conducting conditions, when the electrons bump into each other, that adds to the random motion, which increases the temperature of the wire. It adds to the temperature of the wire. But if they pass through each other and they don't bump into each other, and therefore they don't increase the random motions, then the temperature of the wire stays cold. And so the limitation to conducting is that the resistance to the conducting goes up, and eventually you get to the point where you can heat up the wire to the point where it melts and comes apart. But in this case, the current flows, there's no resistance, and you can put all sorts of current through it. One thing to watch out for, though, is if you have a superconducting wire that's operating, and so you have a high electric current, if for some reason you get some location in that wire where the temperature changes all of a sudden, there's some kind of impurity or something like that, or like a crack, you can imagine that the wire might crack or break near some point. So then at this location or around this location, the electrons now become regular conducting. So you have superconducting electrons coming through, lots and lots and lots of superconducting electrons, and then they hit this, whatever it is, site where there's an imperfection. And now the electrons go from superconducting, where there's no resistance, to regular conducting, where there is resistance. Now you're starting to heat up this area, right? You raise the temperature, and you can raise the temperature now of the surrounding environment to where it breaks apart these pairs, and now a larger fraction is going to be regular conducting, which raises the temperature, which causes more to be regular conducting. So it goes from being superconducting to regular conducting. When it becomes regular conducting, the current increases the temperature, and so it's a runaway growth. You start with something that starts to heat up, and it heats up its neighbors, which heats up its neighbors. So you get a runaway growth of this thing, and the current quenches. So you can immediately shut off this thing, and you have to dump all this electricity, all this energy that's flowing through the wire, immediately gets dumped into heat, and that causes problems. So if you have typically superconducting magnets that you'd use in like MRI machines or something like that, are cooled down to a few Kelvin with liquid helium. But if one of these things develops, then all of a sudden, all that liquid helium that cools everything down, it's used to being at 4 Kelvin, and now it jumps to like 400 Kelvin. It evaporates and can cause all sorts of mayhem. It's really loud when it does it because you typically will have burst disks. You have this liquid helium and it turns into a gas all of a sudden. And so you have to have in your system that's containing the liquid helium, you have to have an interface where if the pressure gets too high, so it vaporizes, now the pressure goes up, and that interface pops out and hits a little, I'll draw a picture of it. I'll try to draw a picture of it. So you have, here is like the side of your pipe. Okay, so now this is a pipe with liquid helium in it. And on the side of that pipe, you'll have this disc. Or I will say, maybe it's not liquid helium that's in there, but this is an escape chamber for gaseous helium. Depends on how you design your system. This burst disc is a disc that looks like this on the outside, and then it's got a little thing stretched across it that looks like that. So it's got like a sharp edge on it, and it's pointed inwards here. As the pressure rises on this side, it actually drives this bulge outward. So it would like to go like that. It would like to push this kind of button outwards, but that button hits this sharp edge and then rips it open, and so it will burst open and allow the gases to escape. So when I worked on an experiment at Fermilab with superconducting magnets and with helium, when the magnets quenched, we had to have a safety system where if we weren't able to capture the helium within the system itself, that helium was able to escape. And so we had this burst disk that would free everything up. So that's kind of cool. Let's see, speaking of superconductivity, do you think that Alan McDonald's discovery of spintronics is good enough for Nobel Prize? I don't know anything about spintronics. I'll say yes, because then it'll be controversial. So I don't know. The LHC magnets fired once because of that superconducting breakdown. Yeah, so that happened at the Large Hadron Collider, where a whole portion of the magnets, because they're all superconducting magnets, because they're like, I don't know what their magnetic field is, like 8 Tesla or 10 Tesla, something like that. So they're huge magnets. They had a whole portion of it become regular conducting, and now all of a sudden the magnetic field changes because the current drops down, and so this ring of 1-ton magnets just all lurched to the side and fell over. That was pretty gnarly. That same thing happened at Fermilab, so they kind of should have known better, because that experiment had already been taken place once before at Fermilab. So the people at Fermilab were like, yeah, that's what happens when you don't listen to us. But it was fun to be around, especially the old grumpy people that they should have, they don't have any respect for us, and as a consequence, whatever. Anyways, so that is superconductivity, is that you pair these electrons up so that they can now have the same quantum state as something else, as another pair of electrons, and therefore the charges can flow through each other without bumping into each other. There was a recent discovery from the University of Nevada, Las Vegas, partnered with a guy at the University of Rochester, where they discovered high temperature superconductivity, and not just high temperature superconductivity, but room temperature superconductivity. So most superconductivity takes place at like 10 Kelvin or lower, really small temperatures where everything is cooled down to the point where the electrons can pair up. You can design interesting ceramic molecules, and they're typically big molecules. If we take a look at high temperature superconductivity materials, if you look at the size of the atoms in these things, so SMFEASOF iron-based superconductors, let's go here and see what else they got. So you can do it with lead. I think you can do it with lead. There are a number of things that will you can do superconductivity with. So mercury, here's lead. Niobium, you can do it with niobium. Tin, I think, is in here. Here's tin, right? And these are all down at this is years. Here's the temperature. So the temperature where it becomes superconducting is like below 20 Kelvin. Okay. Some of them you can get up to like 40 Kelvin, right? So that's kind of cool. If you could get it up to temperatures where you can cool it down with liquid nitrogen is a lot easier to make than liquid helium, and there's a lot more nitrogen around than there is helium. So doing it at liquid nitrogen temperatures, which is like 70 Kelvin, that's a big breakthrough. So you can have all these different substances, but look at some of these substances here that are the high temperature superconductivity. So this is high temperature superconductivity. Mercury, barium, calcium, copper oxide. Excuse me. Notice here that it also says at 30 GPa. 30 GPa is, I think, around the pressures at the bottom of the crust of the Earth. Titanium, barium, calcium, copper oxide. Bismuth, strontium, calcium, copper oxide. So these are big floppy molecules that allow for this high temperature superconductivity. And you're using the structure of the molecule to kind of drive the electrons into these pairs. At higher pressures, you can force the electrons into those pairs. So you can see these different things at high pressures. And notice right here, this dot right here, carbon, sulfur, hydrogen, whatever, so however many hydrogen atoms there were in there at 270 GPa. This is the result that was room temperature. So it's right here around 300 Kelvin. Room temperature superconductivity at high pressure. 270 GPa is the pressure near the center of the Earth. The center of the Earth is like 300 GPa. And this is, so this is right around 300 GPa. But it's a big deal to be able to have superconductivity at room temperature. Even though it's a high pressure that you wouldn't have under normal circumstances, there are things you can do to mimic pressure in these kinds of systems, like doping it and putting strain on the bonds by inserting big atoms into the bonds or something like that, or removing atoms from the bonds and causing strain that acts like a pressure. So anyways, that's high temperature superconductivity. When there is, did I say that? High temperature superconductivity. When there's high temperature superconductivity at ambient pressure, then all of a sudden the carbon footprint of the Earth will drop by about 10%, because you can replace the long distance transmission lines for electricity with superconducting lines. Shouldn't the center of the Earth be zero pressure? Like the exact center of the Earth be zero pressure? No, because you still have to support everything above it. So the gravitational field is zero, but the pressure is not zero, because everything else is acting under a gravitational field that's different. These are some of these sample of high temperature superconductor. You can see how complicated some of these atoms are, these matrices are, and how it forces things into conducting. On this plot that they have tipped sideways, you can see resistivity here, that the resistivity drops to zero at some temperature. So here's the resistance, it goes down as the temperature goes down. But then this one here, the resistivity just plummets. Or plummets from here to here, all the way to zero. Okay, questions to ask. There are some other outstanding large-scale questions that people wonder about. Let's see what it lists here, and I'll add my own to the list. Okay, the universe is open or closed? So this is, what's the ultimate fate of the universe? Is it going to expand forever without bound? Is it going to close itself back up again? Is dark energy going to turn off? There's one of the things that we talked about before is why the universe is so flat. We mentioned this last time. The universe being so flat is a concern. It should be able to pick any number that it wants. Why did it pick the energy density is equal to the energy density? And a solution to that, along with some other issues, like why is the cosmic microwave bound? Okay, so here's us at the center of the universe. We have the CMB over here, and it is at 2.7 Kelvin, plus or minus 10 to the minus 5. And over on this side, we also have the cosmic microwave background, and it's also at 2.7 Kelvin, plus or minus 10 to the minus 5. This light from this side of the CMB has just arrived at us now. The light from this side of the CMB has just arrived at us now. How does this side of the universe know that this side of the universe is at the same temperature? How did they come to the same temperature? That's another question. That's called the horizon problem. And there's a third one that's like the smoothness problem. Why are galaxy clusters the size that they are? And why are they spread out the way that they are? So these questions about why the universe is the same temperature everywhere, even though they're not causally connected, they haven't had an opportunity to communicate and come to the thermal equilibrium. Why the universe is completely flat when it should have some curvature in principle. A solution to this is called inflation. And the idea behind inflation is that if the universe started really small and stayed small for a long period of time, it could come into long period of time, meaning like a tiny fraction of a second, but a long period of time for the age of the universe, or at least at the time, that it could come into thermal equilibrium and everything at that point, and maybe it does have some initial curvature, but then it goes through a rapid period of inflation where it grows in size. And as it grows in size, any curvature that it had would get smoothed out because it's going to grow in size like this. And here's us standing here, and we look and we say, oh, this looks flat. When in fact, maybe there is a small amount of curvature that's left over from its initial curvature when it first started. This also solves the horizon problem by allowing the universe to come to thermal equilibrium and then expanding that. So now everything was originally in thermal equilibrium, and we're just seeing that effect today. And it handles the smoothness problem as well by taking quantum fluctuations and spreading them out. So that's inflation. There's no observational evidence for inflation, but it's expected to be there. I think most people expect that inflation was a real thing. But this would be caused by a scalar field that inflated the universe and then stopped. Inflation stopped at some point. And so one question that we could ask today about dark energy is, will dark energy stop? Maybe it will turn off once it gets, something happens. So we don't know if that's going to happen. We can see that the universe is accelerating its expansion today. We don't know if that acceleration will stop at some point. Is there anything that doesn't move? Anything that's duct taped down does not move. So if you have something that moves and it's not supposed to move, then you put duct tape on it and it won't move anymore. If the universe is flat, why is the Earth not flat? The universe being flat is tells you about the path that light rays take as they go from one place to another. The Earth being flat is not related to the geometry of the universe being flat or not. The Earth isn't flat because, the main reason that the Earth is flat is because it's held together by gravity, and gravity, the force of gravity, squiggles 1 over r squared. It only depends upon distance, and so there's only one shape you can make if you only have one distance to make it with, and that's a sphere. Let's see. I don't know Twistronics either. Windows version 3 million will crash in the blue screen, so the simulation will end and poof, the universe ends. Yes, the universe will end when the simulation ends. All right, let's see what other questions they got. So what is dark matter? We still don't know what dark matter is. How do galaxies form? There are still questions about how galaxies form, what seeds them. What is the nature of various mass black holes? Yeah, what is the origin of black holes? How do you grow supermassive black holes, for example? What mechanism for the energy output of quasars? They have really high energy accelerations. We don't yet know what causes those accelerations of the charged particles that then produce the beams of light that we see. Where do gamma ray bursts come from? There's people in our department that look at gamma ray bursts. Glad you found the stream as well. Okay, here's a question. At very small levels, the universe is spread out. Everything moves, right? Everything moves. There's no zero temperature. You can't. Okay, there's no zero temperature. There is a way of tricking the universe into having a negative heat capacity, and also of having what's effectively a negative temperature. But that requires a weird construction. The idea there is that temperature basically says, the fact that you have non-zero temperature basically means that if you have a bunch of objects lined up, they're going to have kind of random spin orientations. And there's an experiment that was done in the 90s, I think, where they put it in a magnetic field that lines everything up, so now everything's pointed in the same direction. Then they all of a sudden turn it off, and you get a negative heat capacity, which they say you can think of as a negative temperature, but that's kind of a contrived system. Temperature is nothing's completely stopped, and so there's always going to be some temperature. What determines the size of a black hole and keeps it from expanding? Well, a black hole is not a physical, like the singularity at the center of the black hole is a physical object, but what we think of as the black hole itself is not a physical object. It's just a location in space-time where the escape speed is equal to the speed of light. So the thing that prevents it from expanding is simply the fact that is a fixed relationship. There's nothing to cause it to expand unless you add more mass to the black hole. The size of the black hole is just determined by the amount of mass that goes into the center. The more mass you add to the black hole, the larger it becomes. Okay. Is it likely the universe to shrink back on itself if dark matter switches off? Not if dark matter switches off, then it will grow even farther. If dark matter all of a sudden appeared out of nowhere, then you could get it to contract into the future, and then we'd all die in a big crunch. All right, let's see. Intermediate scale. How do phase transitions take place on microscopic scale? Okay, that seems fair enough. Is there a way to deal with nonlinear phenomena that reveals underlying connections? Nonlinear phenomena like direct or linear proportional that makes analysis different. So like, how do you deal with chaos? Is there a way to deal with chaos and solve those kinds of problems? Are there high temperature superconductors? That's a useful thing. What are the magnetic effects of materials we don't understand? Quarks and leptons, are they fundamental? Okay, so this is a good question. If we look at higher and higher energies, maybe the quarks and leptons are actually composite particles in their own right. That would be kind of cool. Why do leptons have integral charge while quarks have fractional charge? That's true. Quarks have charges of either 1/3 or 2/3, while electrons have charges of 1. So that's pretty strange. And we don't really understand why that happens. Are the forces truly equal, unified under certain circumstances? So we talked about electroweak unification. Maybe if you add the strong force to that, are there really grand unified theories? Are there other fundamental forces? Is there a fifth force that we don't know about? Is the proton stable? That's a good question. Maybe protons decay over long periods of time. Are there magnetic monopoles? So I talked about Maxwell's equation, that there might be magnetic charge, in which case Maxwell's equations would have a similar form for the electric field as they do for the magnetic field, where right now they don't. Do neutrinos have mass? That we know. We know that neutrinos have mass. So that's, but we don't know what the mass is, and we don't know the mass hierarchy of the neutrinos. What are the systematic characteristics of high Z nuclei? There's been conjectured an island of stability in nuclear physics. When we do nuclear physics, we'll talk about that. It's been conjectured that there's an island of stability where you could imagine having long-lived isotopes beyond what we've currently discovered. Thank you for that sub. I appreciate that. So these are some questions. Some other questions that are missing from here that I would add is why is there matter? What allowed matter to form in the early universe when there's all this chaos going on and you produce particle-antiparticle pairs? Why are there particles left over and antiparticles are gone? So that's a big outstanding question. It comes through CP violation most likely. That would violate lepton number. It violates some of the conserved quantities that exist. So anyways, all right, let me go. So those are the outstanding questions. Maybe we'll come back at some point and revisit. That's actually a good idea. So we can pick up with some of these after we do the nuclear energy stuff. That might take us through the end of November, maybe mid-December. Maybe we'll pick up with these questions and investigate them as a set of streams in the new year. That would be kind of cool. So we'll come back to that. Anyways, these are some important and interesting questions. Let me go through and answer the questions that are in the chat. And then I'll explain my schedule for the next little bit. When I think of flat, I think of 2D surface not having a 3D component. Since the universe can be described as flat, what does that mean? Okay, so what that means is that when you draw triangles, and I did cover this at the end of last stream, so you can look on my YouTube channel or my Rumble channel, and at the end of the stream I talked about what it means for something to be flat. I went into a little bit more detail. But it basically means when you draw triangles on something, do the angles all add up to 180 degrees? If it's a surface like this, then the angles add up to more than 180 degrees, and if it's a surface that's like that, then the angles add up to less than 180 degrees. And what does it mean to draw a triangle on something? In this case, it's do two light rays that are parallel to each other at some point, do they diverge from each other? Do they impact each other, or do they go straight and keep the same distance from each other? So that's what it means for something to be flat, is the parallel lines never intersect. So can I promo a nuclear waste video from Dr. Konka? Yeah, go ahead and promo the video that you are discussing about. Wow, thanks for those subs. Appreciate it. Should string theory get a mention in these questions? I don't think so. String theory is a theory that's proposed to address these questions, but I don't think it's quite as outstanding. I don't think it's, that's a proposition to solve the dilemma. So these questions that are posed at the end of the book these are the dilemmas that we're facing. Like these are the questions that we want to answer, and string theory is a proposed solution to some of those questions. Are there upper and lower bounds on the mass of the neutrinos? Yes, there are lower bounds on the mass. Let's see, lower bounds is 0. So you can have a neutrino with 0 mass. You cannot have all neutrinos with 0 mass because we know there are mass differences, but you can have at least one neutrino could have 0 mass. So the lower bound is 0. The upper bound right now is like an electron volt. There are experiments designed to measure the mass of the neutrino and determine the mass hierarchy. I have a video and I can talk about it again, but I have a video on Katrin, the Katrin experiment, Katrin, that, again, you can see that on my YouTube or my Rumble channel, where I talk about the upper bound. The upper bound right now, I don't think the best upper bound comes from the Katrin experiment. It might, but you also get a bound from cosmology, where if the neutrinos had a higher mass, then it would affect the expansion of the early universe. Wow, look at all those. Thank you for those subs. Okay, so thanks everybody for coming by. Here is my schedule coming up. I have three proposals that are coming due in less than a month. And so I really need to make sure that I can focus on those proposals and get them in. And so, and especially next week, because there's a bunch of stuff going on the weekend that's preventing me from being able to work on it. So unfortunately, next week I'm going to have to take the week off. Hopefully I can get far enough ahead on my proposals that I will be able to pick things back up on Tuesday, the whatever it will be, Tuesday the 20 something or other, Tuesday the late 20s. So that's the plan, that I'll be back in, what does that make, 10 days from now for that. What I mean by proposals, I'm writing proposals to the National Science Foundation and NASA to fund the research that I do as a professor. So like fund my graduate students and things like that. And so, yeah, they're grant proposals to NSF and NASA for planet formation and exoplanet formation. So that is, do I have a physics explanation for why skydiving is a bad idea? No, I have lots of friends who did skydiving when they were younger. So one more question. Is it not possible that all the dark matter could just be cold, regular matter? We know that it's not cold, regular matter. The reason we know it's not cold, regular matter is because it would affect Big Bang nucleosynthesis. It would affect the ratio of helium-3 and lithium and deuterium that we observe. So if it was regular matter, then Big Bang nucleosynthesis would have persisted for longer. And that was actually the stream that I did last time, was how we know how much regular matter there is in the universe.